And welcome back. In this video, we're going to be taking a look at Chapter 2, Section 5, taking a look at variation. So three things that we're going to do in this particular video. We're going to take a look at direct variation, inverse variation, and then joint variation. So as we take a look initially at the definition of varies directly, or another phrase, directly proportional. Another way to phrase this is the constant of proportionality is another term that comes into play. One of the things we have is we say, let x and y denote two quantities. Then y varies directly with x, or y is directly proportional to x, if there is a non-zero number k for which y equals kx. And k is called the constant of proportionality. So that sounds like a lot of extra words. Really, the only thing that's talking about is we've got two quantities, and they're changing. And so if we take a look down here at the graph of y equals kx, this is very similar to what we saw in another video as y equals mx plus b. That's pretty much slope-intercept form. And in this case, our b value is 0. So we have y equals mx. So really, if m is our slope, and we're going through the y-intercept, we end up with y equals mx, which is the same as y equals kx. So this constant of proportionality here is really nothing more than the slope of an equation. And since we go through the origin, if we're a positive slope, we're going to do something of this sort. And if we're a negative slope, we're going to do something of this sort. Okay? And so that's, in a nutshell, all of our direct variation. Let's do a few examples, though, and see what we can come up with. So the monthly payment, example number 1 here, the monthly payment P on a mortgage varies directly with the amount borrowed. So when we take a look at word problems, I like to go ahead and write on my word problems and highlight some things here. So we've got P varies directly with B. So just from that information here, if my normal direct variation is y varies directly with x is y equals kx, if P varies directly with B, then I can do a substitution. I can say P varies directly now with B in this case. Oops, capital B, let me change that. So now we end up with P equals KB. So we're just doing some change of variables. We're making the variables things that make sense in context. Yes, we can use X and Y consistently. We can use those a lot. But P for monthly payment and B for amount borrowed tends to make a little bit better sense. Okay, so let's see what the rest of the scenario is. So if the monthly payment of a 30-year mortgage is $6.65 for every $1,000 borrowed. So in this information, this 30-year mortgage, that's extra information. We don't need to know this 30 years. What we're interested in is the payment is $6.65, and the amount borrowed is $1,000. So in our question, then, if we take a look at that, if the monthly payment is $6.65 for every $1,000 borrowed, find a formula that relates the monthly payment P to the amount borrowed for a mortgage with these terms. So now we're going to take our $6.65, that's our payment, equals K times 1,000. So if we're asked to find a formula, that is indeed the formula. That's as far as what we need to go. The other thing then it says after that is then, okay, then find the monthly payment P when the amount borrowed is $120,000. Okay. So let's see. If we want to go ahead and figure out a B value, then what we can do is take this equation I've already got circled and let's solve for K. So if we go ahead and solve this for K, we're going to end up dividing by 1,000. That cancels those thousands out on the right side. So K is going to then equal, see, 0.00665. Okay. So now I can take this equation and rewrite it and say P equals, now I know effectively what my slope is. It's 0.00665 multiplied by the amount borrowed. And I know that my amount borrowed now is 120,000. So I'm going to replace capital B with that 120,000. So my payment then is going to be 0.00665 multiplied by 120,000. And once we get to that point, that is nothing more than a calculator activity. We plug that in the calculator, and I had previously calculated this at $798. And so our payment then, our monthly payment on a 30-year mortgage, if we borrow $120,000, in this case, would end up being $798. If we borrow a higher amount of money, okay, so since this is a positive slope, our slope's going to do something like this. So here's my payment. Oops, sorry. Here's the amount borrowed, rather, and here's the payment. And as the amount borrowed increases, so as the amount borrowed increases, my payment also increases. And that seems to be like a logical scenario. So one of the things that hopefully we should see in mathematics is that the mathematics should not complicate what we think about in real life, and real life should not complicate mathematics. They should go hand in hand. So that's a direct proportion. How about an indirect proportion? So we say indirect or inversely proportional varies inversely. So again, we still have two quantities, x and y denote these two quantities. Y varies inversely with x, or y is inversely proportional to x if there's a non-zero constant k, such that y equals k divided by x. So if we are directly proportional, then we have a multiplication, y equals kx. If we have an inversely proportional, then y equals k over x. Okay? And so k then in both of these is a variable, and that's the thing that we're taking a look at. If we try to graph y equals kx, well, let's just say we let k be positive, and if we let x be positive, these are inverses of each other, fractional components here, and we're going to end up with a graph that looks like this. So as x gets bigger, then our y value here is going to get smaller. So they're inverses, they're doing opposite things. Whereas in the other scenario, as x got bigger, y got bigger. Now as x gets bigger, y is getting smaller. We're going to treat questions like this the same way as what we did in this that last example. So let's go ahead and move on to example number 2. Maximum weight can be supported by a piece of pine. So if we take a look at the figure on the left, we've got a, looks like a canyon of some sort with a board stretched across. And so the maximum weight that can be safely supported by a 2-inch by 4-inch piece of pine varies inversely with its length L. So as we just take a look and dissect that first sentence there, the weight that can safely be supported varies inversely with its length. So before we do anything else, I can immediately go ahead and write out an equation. It's supposed to be a k. So weight is inversely proportional to the length, y equals k over x. So experiments indicate that the maximum weight that a 2-foot, or 10-foot rather, long 2x4 piece of pine can support is 500 pounds. So this 10-foot long relates to length, 500 pounds relates to weight. So we can go ahead and plug those in because our next item here says, write a general formula relating the maximum weight in pounds to the length in feet, and then find the maximum weight that can be safely supported by a length of 25 feet. So let's see, so if we've got 500 pounds, we can replace the weight with 500, and our k we don't know, but we do know with 500 pounds we need a 10-foot long board. So if I go ahead and solve this for k, we can multiply both sides by 10. So 10's cancel on the right side. So k equals then, that's a pretty easy mental calculation, 500 times 10 would be 5,000. So I can take this initial equation, now I can rewrite it because now I know my constant here is going to end up being 5,000. So I've got 5,000 divided by L. So my question then is, or at least the question posed to us in the example, is find the maximum weight W. So we will find W that can safely be supported by a length of 25 feet. So that my length is 25. I'm going to say, okay, let's replace L now with 25. And when we do that, what we end up with, 5,000 divided by 25, we can plug that into a calculator. If we plug that into a calculator, I end up with 200, and this is in pounds. So the maximum weight that we could support with a 2x4 that's 25 feet long under these conditions is 200 pounds. As we take a look at a graph of this, okay, our graph would look something of this sort. So we have our length and our weight. As the length of this board increases, the weight that we can support is getting smaller. As the length of our board decreases, then the weight that we can support increases. So that's an inverse variation as far as what we're representing. So we've taken a look at an example of a direct variation, an example of an inverse variation, and let's then take a look at something involving what's called joint variation. So joint variation is when we have multiple things taking place at the same time. Okay, so in joint variations, okay, combinations of direct and or inverse variations can occur. So when we're taking a look at direct variations, that's when we multiply, and inverse variations is when we have a division and we have a divide. Let's take a look at how we can model this. Okay, the loss of heat through a wall varies directly with the area of the wall and the differences between the inside-outside temperatures, and varies inversely with the thickness of the wall. Write an equation that relates all of these quantities. So we've got a lot of things going on here. So we have loss of heat through a wall is going to vary. So let's go ahead and define some variables here. In this particular example, we weren't given any variables. In the previous example, we were told W to use for weight and L to use for length. And in the previous example before that, we were given that P was the variable we're using for payment, and B was the variable we were using for the amount borrowed. So in this particular scenario, though, we are not given any of the variables. So one of the things that we want to do is we want to do what's described as defining the variables. So we're going to say let, L-E-T, and we're just going to use variables. Use variables that make sense. I'm going to use the loss of heat loss, or the loss of heat rather. So I might use H for heat, L for loss. Doesn't matter. I'm going to use L for loss here. So let me say L equals heat loss. And it's going to vary with the area of the wall. So maybe I'll say A is area. Kind of makes sense. Difference between the inside and outside temperatures. So let me say maybe T represents the difference in the temperatures. It's going to vary inversely with the thickness of the wall. Okay, oh, there's another T, isn't it? And so I've got the thickness of the wall, and so maybe I think about that as the density of the wall, perhaps. So I could use a D. Maybe I've got capital T for difference in temperatures. Maybe use lowercase t for the thickness of the wall. I could use maybe W for the wall. And so it varies depending on what we want to use here. I'll use D for the density. Density or thickness of the wall. And again, on these, we could choose any variables that we want. Just a matter of what do we decide to use. We define our variables, then we can go ahead and use them. So we've defined our variables. Now let's write an equation that relates all of these variables together. So the loss of heat through wall varies directly. So L equals K multiplied by all the things that varies directly. So what's varying directly? Well, we've got area of the wall, and we've got the difference between the inside and outside temperatures. Okay, so we're going to end up using then K times A times capital T. Looks like L equals cat at the moment. We get some interesting kind of words that pop up occasionally when we do these. Other items, let's hear and see, varies inversely with the thickness of the wall. So thickness of the wall we said was D. So I'm going to go ahead and divide this then by D. So in this particular question, the only thing that we were actually asked to do was this last part here in yellow, write an equation that relates these quantities. Well, we have that. This is the equation that relates those quantities. We have a direct variation with A and T because it's getting multiplied by K, and we have an inverse variation with D because K and D are getting divided by each other. Let's take a look at a couple other examples. I've got three more examples here I'd like to take a look at, and these are items that are going to be similar to what we might see in our homework assignments, might see on a quiz or a test. Example number 4, the force of the wind on a window. So the force F, okay, so now in this case we're getting some variables defined for us. So we've got the force F of the wind on a flat surface positioned at a right angle to the direction of the wind, varies directly with the area of the surface and the square of the speed. So let's see, so square of the speed V. And then a wind 30 miles per hour. Okay, so let's take a look at here. So this first part here is going to give us then our initial equation. Okay, so we've got the force F of a wind, position is right angle to direction of speed, varies directly. So that's multiplied by the area um, of the surface and the square of the speed, v. So the square of the speed, if the speed is v, the square of the speed is then v squared. So a force equals some constant multiplied by area times v squared. So velocity, we're going to think about it that way. Let's take a look at the rest of our scenario here. Then it says a wind 30 miles per hour. Okay, so let's see here. So wind 30 miles per hour. So we have a value now for the wind speed. Okay, so that is our speed. So let's see here. So that would be, if I start filling things in, that's going to be 30 squared. Blowing on the window, measuring 4 foot by 8 foot. Measuring 4 feet by 8 feet. So that's an area, isn't it? Okay, so my area then is 4 feet by, what do we say, 5 feet. So my area then is 20 square feet. Okay, so I've got 20 in there. Has a force of 150 pounds, so that's my F. Okay, so 150 pounds, and I still don't know my K. What we can do then is we can solve this equation here for K. Then we know our constant, because what our question is going to be asking us then is what force does a wind of 50 miles per hour exert on a window measuring 3 feet by 4 feet. So before we get to that green piece, we have to go ahead and finish up this equation, and let's solve for K. So if I solve for K, let me get my pen back. I got 150 equals K times 20 times, let's see, 3 squared is 9, and 10 squared is 100. So it's going to end up being 900. Do some mental math on something of that sort. And so 100 equals K times 18,000. And so if we divide both sides by 18,000, then we'll figure out our value for K. And this would be something, I'm not going to be able to do that in my head. That's something I would go ahead and plug into the calculator. And so we got 150, let me pull my calculator out back over here. 150 divided by 18,000, and we get 0.0083, and the 3 repeats. One of the other things we might do, since we got a repeating value though, is let's go ahead and reduce this fraction. So I've got 15 over 1800, and if we go ahead and reduce by 15s, then we end up with 1 over 120. So there's my constant. So now I can go and put that back into this equation. So let's see. So F equals 1/120th. Let me put that 1/120th times A times V squared. Now we can take a look at the rest of our question. So what force does what force does a wind 50 miles per hour? Okay, so that's our speed. Exert on a window measuring 3 feet by 4 feet. So that's area. So 3 feet by 4 feet is going to end up being 12. So 12 square feet is going to go in here for A. So we got the force is 1 over 120 multiplied by 12 multiplied by 50 squared. And then when we get to this, on this, we really could just plug that all directly into the calculator and just come up with a final response. And on this one, we do end up with 250. And so that would be our force that we are applying onto this window. And so given our scenario then at the beginning, we had, what we were told was the force of the wind on a flat surface positioned at a right angle. The wind varies directly with the area of the surface and the square of the speed. So given our initial information, then we end up writing our equation, solving for K, and then using our other information and plugging in values for our variables. Then at the end, we have the variable that we were looking for, in this case, force. 2 more examples. These examples are in the textbook as well, in the exercises or homework material. So this first one is number 25. Obviously, the second one is number 28. And let's see if we can go ahead and figure this one out. So the distance s that an object falls is directly proportional. Okay, so immediately I've got some variables here. So distance s, object falls, is directly proportional to the square of the time t. Okay, so let's see. S equals k multiplied the square of time, so t squared. So s equals kt squared. If an object falls 16 feet in 1 second, okay, so 16 feet in 1 second, so that's the distance s, and 1 second is time. Okay, so if that happens, how far will it fall in 3 seconds? So in order to figure out how far it will fall in 3 seconds, we have to figure out first this value for k under the initial conditions that we know that it falls 16 feet in 1 second. So if we plug these things in, so 16 feet in 1 second is going to look like this. 16 equals k times 1 squared. So 16 equals k. So looks like 1c there. There we go. So now my constant is 16. So I can take this initial equation and say, okay, now I know my k value. So I've got s equals 16 times t squared. So then my question becomes, how far will it fall in 3 seconds? Okay, so if I let my time here now be 3, then I can say I want s equals 16 times 3 squared. If we do that, then we've got, again, we could plug all of this into the calculator. 16 times 3 squared is 9, and so s 16 times 9 is 144, and so that we're talking about distance here, so that was going to be in feet. So our one question, how far will it fall in 3 seconds, is going to be 144 feet. We do have a follow-up question here. How long will it take for an object to fall 64 feet? So if that's the case, again, we can go ahead and take our initial equation here, because we know it's s equals 16 now times t squared. So how long will it take? That's our t. So we don't know t in this case, but we know it's going to fall 64 feet, which is our s. So we know then 64 is going to be 16 times the square of time. Solving that equation for t squared, you have to divide both sides by 16. So 64 divided by 16 is 4. When we go ahead and try to solve this, we're going to take the square root of both sides. So in an equation, we've got the principal square root and the non-principal. So t is going to be plus or minus 2. So how long will it take the object to fall 64 feet? We would say 2 seconds or negative 2 seconds. Now in context, negative 2 seconds makes 0 sense. So what we would say then is we would ignore this negative, and we would just say time equals 2. Time equals 2 seconds. So in 2 seconds then, 2 seconds, how long it would take this object to fall 64 feet. So some questions related to time here in physics and some falling objects. Later on, one of the things that we'll do in the course is we'll take a look at this s equals k times t squared. Whenever we have an item squared, we end up with a quadratic. It ends up some fascinating kind of material, and that'll be a little bit later in the course. Let's take a look at this last example then for us for today, number 20 at least for this particular video, physics of vibrating string. Okay, so the rate of a vibration of a string under constant tension varies inversely with the length of the string. Okay, so we have the rate of vibration varies inversely with the length of the string. So in this case, we were not given any particular variables. As in the last example, we were told, s was going to be the distance that we fell, and t was going to be the time. We don't have anything in this case, so we have to define our variables. So let's see, r equal the rate of vibration. And again, we could have chosen different variables instead of r being the rate of vibration. Maybe I chose v for vibration. Okay, different things we come up with. And I think L makes good sense for length. So we got the length of the string. And since we know this varies inversely, we know that these are going to end up being a division. Let me make sure my R looks more like an R, not a K there. So my rate of vibration varies inversely with my length. So now if, okay, So if a string is 48 inches long and vibrates 256 times per second, what is the length of the string that vibrates 576 times? So then we end up with this question here. So what we have to do is we have to take a look at that blue piece first. 48 inches long, vibrates 256 times per second. So we're going to fill in the material here, the other variables, so we can find K. We got to find that constant. And that's that same pattern we've been taking a look at overall. So the 48 is my length, and 256 times per second is a rate. And if I go ahead and solve this, I can multiply both sides by 48. The way on the right, they go ahead and cancel. So K is going to equal 48 times 256, and plug that in the calculator. That works out to 12,288. So now I can take this equation and I can fill in K. So that's going to be 12,288 varies inversely with length. Okay. So what we just did down here is we used all that information to find K. Now we're going to go ahead and figure out, well, what is the length of the string? Okay, we're going to try to find L here. That vibrates 576 times per second. So 576 is a rate. So 576 equals 12,288 divided by L. Now, in this case, we're trying to figure out L, and this is the first question that we've had where our denominator holds the variable. So we don't want our denominator to hold the variable, so several different things we can do. One of these is I need to get that L out of the denominator's position. So this bar here, that fraction bar, means to divide. So to get rid of the division, we can always multiply. So what if we multiply both sides by L? What that does then is that moves the length over to the left side. 576L equals 12,288. Now I can come back through and divide both sides by 576. So on the left side, those things cancel. The 576 cancels. And we have our length. So our length ends up being here. If I divide these out, I get 21.3 repeated. So that's 21 and a third. And let's see what our unit was here. All our units here were in inches for length. So this is going to end up being 21 and 1/3 inches. Okay. I'm going to try to fix that a little bit nicer. It's 21 and 1/3 inches. Now, when we're in homework, when we're taking a look for MTC and we're using Pearson's My Math Lab on this one, if it asks for an integer or a fraction, then or a decimal, we got to figure out which one we're looking at. If we're looking for an integer or a fraction, okay, 21 and 1/3 is both an integer and a fraction. So we would have to take the 21 and 1/3 and convert that. Let's see, so sometimes we call this the C method. I got 3 items in a whole, multiplied by 21 wholes, so that would be 3 times 21, and then plus I got 1 part overall. So that would be 63 plus 1, so that would be 64 thirds. Okay. So I should still put this over 3 overall. So 21 and 1/3 is the same as 64 thirds. If it asks for a decimal rounded to so many different places, then we would go ahead and say, oh, well, that's 21.3. However many places that it wants, that's 3 repeated. So it wants 2 places, we do 3, 3. There's only 1 place, just 0.3. And we have to figure out, what are we asked for? So if you end up with an answer and the computer program says, oh, no, that's not correct, it might be that we need to take a look in the, typically it's in a blue typeface behind the answer box. It'll tell you what to look for. Sometimes it's given in the question as far as round to the nearest, whatever, and then it'll tell us those pieces. So we do have to be aware of those components. So summarizing what we did today then, let's scroll back up here to the top, move this over to the side. We looked at then section 2.5 on variation. We took a look at direct variation, which we have multiplication, inverse variation, let me do it this way. So this is y equals kx, inverse variation, which is y equals k divided by x, and then we could have joint variation, where we could have maybe multiply by x and divide by w. So we end up with multiple scenarios. Okay, so that's it for this particular section, variation. And if you notice a mistake, please let me know. Otherwise, I'll see you in another video.